So we're going to talk about risk ratios today, and it's you might be asking why this, why now, and as you'll see, this actually after we were talking about ROC and goodness of fit, this actually makes a lot of sense. And when we see how we go about estimating risk ratios in logistic regression, it builds on some of the concepts, particularly from ROC curves. And we've spent all the time up until now in the course talking about odds ratios, more or less, in the logistic model. And as we'll see, it doesn't really always make sense to calculate an odds ratio. It's kind of a weird quantity that really we epi folks made up because it's convenient. But actually, risk ratios are much more useful in life, and it's just not as native. It's not as native to the logistic regression model. But we're gonna manipulate things to make it work. And if we have time, I really, really hope we have time. But I love to talk, so I hope we'll see what happens. But I really want to go to SAS to show you something really cool, which is something I wrote last year to actually conduct a lot of the things we teach in this course automatically. And make pretty pictures and things like that. So I want to try to get there today. And if not, I'll find a way to get the information to you. I might hijack a piece of the next class. So this is going to be our last topic before survival analysis. And then next week, we're going to jump into survival analysis. Dr. K is going to take back over for the start of that. And so today, we're going to talk about, I'll make this big. Now it's big. Why the risk ratio? Why do we want to do this? And then we're going to talk about how to go about estimating the risk ratio using logistic regression. And to really appreciate where it's coming from, we're going to first talk about linear regression, which really is often the way to, it's often easier to show a concept in linear regression and then make it, then build it up to logistic regression. So we're going to start there. And then I'm going to talk about some standardization methods. There's kind of 3 standardization-based methods. I'm going to go into detail on 2 of them, conditional and marginal methods. And the last one is the stratified method, which I'll have a few slides on. Where we're going to go is that this one's really cool. Okay, this one right here, the marginal method. Everything, because it's, epidemiology, everything has like 6 names. So these things also go by the predicted or predicted margins methods, or the marginal method, and then conditional is also called the conditional or observed margins methods. So the conditional margins or observed margins. We're not standardized here in our names for things. And we'll talk about how to do this. This lecture is going to be very applied. It's going to be very much like how to do it. And we'll see that for both of these methods, that Sudan is actually a better package to use than SAS. So I'm going to talk about how to use Sudan. But it's going to be Sudan inside of SAS. So it's just a little bit different code. Your life is going to be otherwise the same. So you'll see. And then I'm going to end with some other alternative methods. In the literature, there's a lot of this, the log binomial method. And so we'll talk a little bit about that. It's actually a different model. It's not a logistic model. So I'm going to focus mostly on how to do this in the logistic model. So, all right, here's this data set that we've beaten into the ground, the MRSA data set. And here's the 2x2 table for that. Right, so the outcome here was having a resistant staph infection. That's on the rows in this piece here. And then the exposure was previous hospitalization. And this is what that data set. This is the 2x2 table. Okay. So here, what's the risk of having MRSA? Well, it's calculated on the columns, right? And I put an asterisk there because the study is actually cross-sectional. So it's the prevalence technically, but let's just call it the risk. Right? And the reason I feel okay saying that is because the hospitalization was previous, so it's kind of the risk, maybe. Just go with it for a moment. We can call it prevalence ratio too. But we compute the risk of having MRSA in the columns, right? So 103 over 178, 58% of the previously hospitalized develop MRSA, compared to the non-previously hospitalized, and it's 11%, 12 over 114. Okay, so that's the risk. Okay, and you can compute this thing called the relative risk, right, as the ratio of these 2 pieces, and that's 5.5. I'm using this notation here to mean risk. This is the estimated, that's why it's got the hat, the estimated probability of the disease given your exposure is 1. So this is the way I'm just kind of writing it here generically. The risk of the disease given you're exposed is 58%. And the risk ratio is the ratio of these two things, probability, right, the probability given of the exposure of the disease given you're exposed over the probability of the disease given you're unexposed. Okay, 5.5. All right, well, lo and behold, if you remember way back on day 1, we said the odds ratio was 11.7. Okay, and on the same data, same 2x2 table, but the odds ratio is 11.7, so much higher than the risk ratio. And the reason for this is something that is an Epi1 concept, which is that when you have a non-rare outcome, the odds ratios are always inflated relative to the risk ratios, and they get, right? And remember, there's this thing about like rare diseases and all that, rare disease assumptions, and that whole idea was that when the thing is rare, the outcome is rare, the odds ratio and the risk ratio are kind of close to each other. But often in life, we're not necessarily dealing with rare outcomes. And you get things that look like this, and these are really just different. I mean, they're both showing positive association. The statistical tests that you use on the null value of 1 are always the same, which is why we feel okay testing odds ratio equals 1. That's because it's also testing risk ratio equals 1. That's another Epi1 thing, or Epi2 lesson from the spring. So, you know, they both, the hypothesis tests tell the same story, but the real thing that we actually care about is really the risk ratio, right? How much more at risk is this group relative to this group? That's the relative risk. And the odds ratio gets at that idea, but just not as directly. It's not actually the risk ratio. It's this thing called the odds ratio. So, and it tends to get really big unnecessarily. So, you know, the odds ratio is really not, again, we care more about the risk ratio. It's easier to interpret. The language we use for the odds ratio is basically lifted from the risk ratio, right? We basically say things like people that were exposed had 4.1 times the chance of developing disease. We use the language. When we talk about odds ratios, we really wish we were talking about risk ratios, and our language kind of reflects that. We say it's this much times the risk, but it's actually the odds, right? The ratio of the odds is this much times that ratio of the odds, and that's really wordy, so we don't even say it usually. We actually often say the risk ratio words. So this is, you know, this is my case here for we actually care about the risk ratio, right? And we get away with the fact that the hypothesis tests are the same. So it kind of gives us protection. So we're not saying like totally the wrong answer because we know that the risk ratio is not 1 when we say the odds ratio is not 1. But the reason, you know, one of the times you have to use the odds ratio is when you're doing case control studies, right? And the reason for that, as motivated in previous EPI courses, was that the case control study is funny because we manipulate the risk directly by sampling cases and controls, and you can't estimate the risk out of a case control study. So you have to do this voodoo where you measure odds ratios, and then you there's this elegant way of showing that the exposure odds ratio is the same as the risk odds ratio, and then that kind of sort of with under rare disease assumption equals the risk ratio, right? There's this dark art that goes on. I think we show it in the beginning of 534 last semester to show that the odds ratio in a case control study basically gets you to the risk ratio, and that's a good thing, and we have to compute the odds ratio. For the other study designs, we really would rather not have the odds ratio because what we really care about at the end of the day is discussing the risk ratio, the relative risk, and we just often back into it with an odds ratio. Or the prevalence ratio. So if you have a cross-sectional study, you're not measuring risk, you're just looking at the probability of the outcome, you know, the prevalence of it. And you're not going to maybe hang that word risk, which implies kind of a causal prospective thing. You might say the prevalence of the outcome. But for either the cross-sectional or the cohort type or the trial kind of prospective, those kind of designs that are not case control, we'd rather talk about the risk ratio and the prevalence ratio. We just, we have it stuck in our heads as EPI folks that we care about the odds ratio. And the logistic model natively e to the beta is the odds ratio. It's not the risk ratio. So there's a mathematical convenience, and everything's kind of built around it. But we're gonna break that down. So so there's a problem. Like, why aren't we doing the risk ratio? Why aren't we doing this? So so there's a refresher why it's easier to do the odds ratio. Here's a standard EV. Here's an EV model: alpha plus beta times exposure, and then here's a whole bunch of V's. No EWs. Okay, in the logit form. So a basic logistic regression model with no interaction. So the odds ratio, right, was this. Here it is. Okay, right, e to the beta. There's no interaction. There's no interaction. It's e to the beta. And the reason was, here's the odds of disease given you're exposed, and some V's, was this. Was e to the alpha plus beta exposure plus lots of V's. And the odds of the disease given unexposed is the same expression, but without the beta times exposure. And we know that this kind of all cancels out, and what you're left is with e to the beta. Okay, so that was odds over odds is odds ratio. Everything cancels out. Okay, well, what's the risk ratio? So the logistic model, right, has a logit form, and it also has the risk form, this thing that spits out the probability of the outcome. That's the risk. And that's this, 1 over 1 plus e to the minus, some stuff. And when you're exposed and you have some V's, this is what that looks like, 1 over 1 plus e to the minus alpha plus beta times exposure plus the sum of the V's. And when you're unexposed, it's the same thing, but without the beta times exposure. And so to take a risk ratio, I would just take the ratio of these two expressions, and it doesn't cancel out. This is what you're left with. You put one over the other, and you get 1 plus e to the minus alpha plus the sum of this stuff, and then the same on the bottom with beta exposure. And so you can't actually there's no convenient way to take this ratio. The V's don't cancel out. You're just left with this not very helpful expression. And so the big fundamental issue is that the risk ratio depends on the actual V's involved, on specifying out all of the V's. Okay, so the odds ratio, the beauty of the odds ratio is I didn't have to think about, oh, what sex are they, or what this, or what that. Everything cancels out, and the odds ratio for exposure was independent of all the other stuff. The risk ratio is explicitly dependent on all the other stuff. Right? Somebody's risk, turns out, is dependent on all these other things going on in their life, right? What their age is, what they're this, and those things have to be specified, and you can't just cancel it out. And so that's reflected here. So everything else that we're going to do to get the risk ratio is going to be clever ways of plugging in the V's to deal with this problem. Okay, so this is the fundamental issue. We can't just ignore the V's. We got to specify other people. We got to specify what the V's are to compare exposed and unexposed. Okay, and so what on earth do we plug in? We have a data set with 300 people, all of which have different V's. What do we plug in to this formula to get something that we can call the risk ratio for the sample? Everyone's different in the data set, so what are we going to plug in here? And so we're going to talk about the methods for doing that. So we need to specify the V's. And it turns out the odds and the risk ratio are all things that we get out of a logistic regression model that required the V's. The only thing that does not require it is the odds ratio. The odds ratio, everything cancels. So what we want to be able to do is compute this risk ratio thing for all of our data. And it's going to involve plugging in some stuff for the V's. And it turns out this has been dealt with in linear regression, and this was I don't think it's quite covered exactly this way in EPI 591, but it's in the book, and you may have seen this thing called the analysis of covariance. And it's basically a linear regression model. So it's very similar to ANOVA. Do people remember what the ANOVA model is? It's basically linear regression with only categorical predictors. That's the summary. That's what ANOVA is. Okay, there's no continuous variables in your model. And there's this thing called the analysis of covariance, which is, again, another type of linear regression model, which is a model that has continuous and categorical covariates. So it could be a model that looks like this. Y, continuous y, it's a linear regression model, is equal to alpha plus beta times exposure, a categorical exposure, two levels to it, plus adjustment for some other continuous v variables. Let's say it's age, it's blood pressure, or whatever. And there's this assumption in the ANCOVA, if this is in the linear regression book from last semester, that they're parallel. There's no EW terms. So this could be, for example, this is a very simple analysis of covariance model. Okay, a linear regression model. Here's the line for, they're the same intercept, let's say, sort of, because I'll get to this term. They have this. It's a simple linear model in some sense. There's a beta times exposure 1 or 0, and then there's another term. Let's say we're adjusting for a single confounder. Let's say it's age, and this is what the regression models could look like. When you're exposed, the line's up here, let's say, and then when you're unexposed, the line's down here. This is a continuous covariate, so we can plot it as like a line, y times v, y times age. And when you're exposed, the line is higher. There's a difference up, down. In this beta, you add beta, and it goes up or down. And then when you're unexposed, it looks like this lower line. Remember this idea in linear regression, when you have a change in the intercept, it goes up, the line just shifts up or down. And so, oh, here it is. It's what I just said here. Here it is. I don't have to do my hand thing. If you had a linear regression model with a single continuous variable, I'm going to call it the v variable, is continuous, and then a dichotomous exposure, it always looks something like this, 2 lines, and then the difference between them is beta, and that's the change in the intercept associated with the exposure. This is the effect of exposure. It shifts the line up or down. Okay. And in linear regression, we're often very interested in this thing called y bar. Y bar, does that sound familiar? Y bar, the mean value of y. Yeah, that was the thing of interest often in linear regression. The mean value of y. Okay, it's not, it's y is continuous. It's just, we're not interested in risk, but now it's the average outcome at, let's say, exposure. And so. Anyway, we often would compute this thing in linear regression called the y bar, and it was estimated in the linear regression model like something like this. What's the average value of the outcome for someone who's exposed? Well, what you would do and I hope this came up somewhere in linear regression, is to get the average value of the outcome when you're exposed, you use the regression model and you say alpha hat plus beta hat. So this is, again, what SAS would spit out. And then plus the gamma hat times the average value of the continuous covariate. This is the way you do it in linear regression. So, right, we want to get some kind of summary measure out of the model for what the effective exposure is on the outcome. One way to do it is you compute what is the average value of the model at from what is the average value of the outcome given the coefficients that SAS says at the average value of the covariates. So we have to make a choice here. In your data set, let's say this was age. People have all sorts of different ages in your data set. Right? There's like all sorts of different ages here. And some people are exposed and some people are unexposed. What you would do in linear regression is you would compute the average age of the data set. We're going to call it V bar. And you plug it into this model here in these two ways, and that gives you the average value of y when you're exposed is this, at the average value of age, and the average value of the outcome when you're unexposed is this expression, again, plugging in the average value of age. So all this is to say that in linear regression, the way you would have done this is you'd have to compute the average value of all of the other control variables, and you plug it into the expression. And that's the way in linear regression that you estimate the average value of the outcome. So the basic idea is, like, again, we have people with all sorts of different values for the v variables, and the simplest thing to do is you plug in the arithmetic mean of all the continuous variables in the data set, and you get these you get y bars. Often you compute the differences of these things. That's often what happens in ANOVA, and in linear regression you compute the differences. Or you can compute this weird thing called the mean ratio, which no one does, but you can imagine you could make this thing called the mean ratio, okay? That's the average value of the y's when you're exposed over the average value of the y's when you're unexposed. And it would look something like this. No one ever does this, but this is going to be analogous to what we want to do for the risk ratio. So you use the model in some way. You use the model estimated coefficients, alpha plus beta, plus all of the gammas times the average of of each of those other covariates, all the other potential confounders. We compute the average in the data set, and then that becomes the average effective exposure. So you're making like an average person. You're not plugging in like you're a male, you're this or that, this is your weight, this is whatever. You take the average of all the covariates in the data set and you plug them in, and that's one way to come up with the average value of the outcome in the model. Okay? Does that make sense? It's kind of weird. So one solution, effectively, back to this fundamental problem of what on earth do you plug in for the V's? One potential solution is compute the mean of the V's in the data set for everyone, okay? And then just plug in across the whole data set what those means are. And now that lets you compute this expression of comparing the exposed and the unexposed. You're going to do it at some average person. This average person has the mean of every V variable in the data set. And in linear regression, that is like the thing you do. And I'm going to show you that this is a thing to do in logistic regression, but there's even a better thing to do, which we'll talk about, which is the marginal approach. So the analog of this weird thing that we just talked about is called the conditional marginals method, or the conditional margins method. And it's this equivalent of the analysis of covariance, but in the logistic regression model. Instead of computing the mean ratio, we're going to compute the risk ratio. And it's going to be the logistic formula, the ratio of two logistic formulas. This is the probability of the outcome when you're exposed over the probability of the outcome when you're unexposed. This is just the logistic regression equation, and here we have exposure, here we don't. And what we're going to do is we're going to plug in alpha and beta hat and all these pieces as usual from the SAS output. Okay, and then what we're going to do here is plug in the sample means of all of the potential confounders. Okay, so one simple best guess is just put in the mean for everything over here. So, e to the beta just was e to this beta hat. Now we're going to need also the intercept, because the intercept doesn't cancel. Nothing cancels. So we're stuck with the intercept twice. We have to plug in the intercept in the numerator and the denominator. And we're going to have to plug in all the gamma stuff that doesn't cancel away. So everything else used to cancel. Now we're going to need all of the SAS output to actually compute this thing. It's not as simple as e to the beta. And the best guess of what to plug in for the V's is going to be the sample mean for all the V's. Are we on board? Things don't cancel, so now we use everything. And we're going to take a best guess for the V's, which is the means. There's some problems. This is going to be weird. I think there's even a thing that says weird. Strange. It's going to get strange. So here's the idea, right? We're going to compute this thing. We're going to plug in the sample means. The weird thing is that, like, often, as we've dealt with, the V's are categorical. Right, 0, 1, smoking, not smoking, or whatever. Here's the example of smoking, not smoking. So if 22% of the sample smokes, then the mean of that is 0.22, right? 22% of the data is going to have a 1. The other 78% is going to, 78% is going to have a 0. So the mean of the 0, that column of zeros and ones, is going to be 0.22. So that makes kind of sort of sense because 0.22 is the prevalence of smoking, right? In some sense, so that makes sense. You're going to plug in 0.22 for the V bar, but no one in the data set has a 0.22, right? You're plugging in kind of a fictitious value, right? The data set's full of people with zeros and ones, and instead you're going to come along and put in a 0.22 into your formula. So it's kind of weird. That's strange. It's kind of strange. You're plugging in kind of unobserved values. You're kind of interpolating. The data only has zeros and ones, and you're going to go along and plug it at 0.22. And that wasn't really ever observed. It is the model valid at this thing in between 0 and 1. Or better yet, think about 3 levels of smoking. This is even weirder, right? What if you had 3 levels of smoking? A totally nominal, unordered, categorical thing. Never, current, past. Okay, let's just do that. Okay, so past would be not current, but only past. Okay, so now you have 2 dummy variables. Okay, and the reference, let's say, is never smoked. V1 is past smoker, and then V2 is current smoker. I made up 15% were past and 18% are current. Then you're going to plug in 0.15, 0.18, and that's going to represent the average smoking situation in the data set. Well, that's kind of weird because no single person in the data has anything above 0 for both of those. You're either a past 1, 0, or you're a current 0, 1, but you're never a 0.15 and a 0.18. So there's some funk to this. Like it lets you, you're going to get an answer, and it's like people use it. But there's like some validity issues because there is no such person that's actually in both states at the same time, and let alone fractional. Right, I'm 15% a past smoker and I'm 18% a current smoker. It's a little odd. So it's just odd. So, but this method gets an answer, and Sudan and SAS both will give you that answer. So here we go. So, we're going to talk about here's the MRI example, and let's think about a V variable being previous antimicrobial. Previous antimicrobial use was one of the V variables considered. So I'm stratifying here. And I'm showing the stratified 2x2 table on this V variable, and here's our exposure and our disease. And we're going to look at what SAS kind of gives us for this situation. And here in the stratum of V equals 1, where you have previous antimicrobial use, the effective exposure is, the risk ratio in that stratum is 3.53. And in the PAMU 0 stratum, it's 2.94. Okay? And first of all, does this kind of bring back memories of the Mantel-Hansel approach? Remember we used to do this kind of thing? And the whole idea of the Mantel-Hansel approach is a totally other way to deal with this, but without logistic regression. We're going to get a risk ratio with logistic regression. But remember, Mantel-Hansel was going to give you break it out by the V's, and then you smush it back together in some way to get an average risk ratio that's basically somewhere in between these two, right? That's what the Mantel-Hansel approach does. You stratify on the V's, and then you pack it back together, and you get an answer. So we're going to basically this logistic approach is going to be simulating that in some sense. Anyway, so what is V bar? Well, V bar in this data set, when the V is PAMU, is 155 over 155 plus 135, or 53%. Why is that? Because look at this total. There's 155 folks that have PAMU, and 135 folks that don't. So the prevalence of PAMU is 0.5345. This thing we're going to plug into our logistic-like expression, and we're going to get a risk ratio. And we probably expect it just on how we know on how this behaves. The answer is going to hopefully be between 2.94 and 3.53, right? We hope it's just like what Mantel-Hansel would tell us, and what you hope the answer is somewhere in between here. So so V bar is 155 over the sum of those two, and it's 53%. Okay, so let's do it. Here is the output of SAS when we fit a model that has just previous hospitalization and PAMU. Here it is, intercept, ta-da, beta, and then the gamma 1, whatever. You plug it into this expression. Here we go, 2.46, negative 2.46, that's the intercept. And here is the beta, and then here's the gamma for PAMU. Okay, there it is, times 0.53. What's 0.53? It's this, V bar. It is the average amount of PAMU in the data set. Okay? So that's this business. We're going to plug in the average value of the confounder. Again, it's weird because it's neither 0 nor 1. It's somewhere in between. Okay? Now, the denominator is the same expression, 1 over 1 plus e to the minus blah, 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 but not with the exposure. Right? That's the whole point. It's exposed versus unexposed. Okay? And you get 0.488 over 0.156. That's the risk of the exposed over the risk of the unexposed, according to the model. 3.13. 3.13. That's pretty That's pretty cool, right? It's between 2.94 and 3.53. So just by computing the average value, by running this model and computing the average value of the V variable, you can get an estimate of the risk ratio. Okay? So this wasn't that much work, right? This wasn't so bad. It's a little more work than e to the beta, but not horrible. And now you have something that's probably a little more useful than the odds ratio, right? The odds ratio is you basically inflating the number to look better. And now you got a more realistic number that's actually the thing you care about, which is the risk ratio, which is 3.13. Okay, so all you needed for that was the SAS output and the average value of the V's. Okay, how do we do this? How do we get the computer to do this? There's actually ways to do this faster. Faster way is to use an estimate statement. So the estimate statement we've used to compute odds ratios before, but you can actually it can do all sorts of cool things. And what you can have it do is, the estimate statement is a way to have the coefficients in the model multiplied by anything. Right? It's much more robust than just the way we've been computing odds ratios. And it's a way to say, hey, multiply the alphas and the betas and the whatever by any other coefficients. And so this, if I say, estimate the probability of disease given exposed, this is a label, intercept 1, well, okay, this is weird. We never used to have the intercept, because the intercept used to cancel in the odds ratio expression. But if I say, this is a special magic SAS word, intercept, it knows what to do with that. You say intercept 1, pre-hosp 1, that's the exposure. Then PAMU 0.5345, that's the average value business that we've computed already. Imagine you used proc means or whatever to compute this. Then the next line, you do intercept 1, previous hospitalization 0, because it's going to go away. Or you can leave it out. You can just leave it out and it's a 0. And then PAMU 0.5345. So what you're telling SAS is this. You're telling SAS how to do this. But you're not plugging in 2.46. It's going to do that. It's going to go find the alpha hat and the beta hat and all of that. You're telling it what it's multiplied by. So you're saying alpha times 1, beta times 1, gamma times 0.5345. Okay? So I'm pointing out the special things that make this different than the odds ratio expression. The odds ratio required you to not, you didn't want this for the odds ratio. This is plugging in the V-bar. And this thing, iLink, is not like a Mac product. This is the inverse link. And what that means is I want this on this probability scale. Normally, SAS gives you things on the logit scale. All of the output is on the logit scale. Which is that alpha plus beta, blah, blah, the linear-like expression. This says, I don't want logit. I want it to look 1 over 1, basically compute 1 over 1 plus e to the minus blah. I want you to compute that function on the result. So this says, give me 1 over 1 plus e to the minus, this times 1, this times 1, this times 0.5345. Okay, you do that, and SAS gives you this little table of output. Ta-da. It gives you this thing that says estimate. This is the logit scale This is the logit scale result, and this is the iLink on the probability scale, 1 over 1 plus e to the minus. This is this 0.4884 over this, which by the way is exactly this. The thing we computed manually, it did it automatically, and you can just take the ratio and get 3.13. Okay, so this is easier than the previous way, still a little work. Right? It's this work because you had to type this out and you had to do this. I'm going to make it easier and easier for you. This is like this is the semi-automatic. Like otherwise it was totally manual. This is the way that's like a little get in there, and then we're going to go to fully automated way to do it. I don't like computing V's, right? V bars. This is annoying. I'd rather not have to figure this out. So you can actually do another trick in SAS using the LS mean statement. Do people remember this from linear regression? Does that use it all? No? Oh man. We'll have winter break camp and we'll go over linear regression Eli's way, and we'll do LS means. Because you obviously have nothing better to do. So you can use this thing called the LS mean statement. The LS mean statement is this magic statement in all the SAS regression procedures, and what it does is it computes the mean value of y. It's okay. And the mean value of y is useful in linear regression, as we talked about. It's also useful in logistic regression because the mean value of the y is the risk. The outcome is the risk in linear regression, in logistic regression. And what this statement says is the following. Almost here. It says, hey SAS, I want the mean value of the outcome at all levels of previous hospitalization. Okay, that's the exposure. Give me the mean value of y at every value of e. So e is 1, e is 0. So it's going to give you 2 lines. This thing, ohm, is not about like yoga. It's about the observed margins. And what that means is plug in the observed mean of every v variable automatically. That's good. It's going to compute for every variable that's not here, it's going to plug in the mean automatically. It's the observed margins, the observed mean. And iLink, again, it's going to give it to you on the probability scale rather than on the logit scale. And that's exactly what we want. So automatically, SAS is going to do, for every value of previous hospitalization, it's going to give you the mean again, and you can get 3.13. Okay, so this is cool. And you have to put the class statement in, and you have to use param equals GLM. This is a different way of coding dummy variables, and this statement will only work if you tell it to code the dummy variables using the GLM way. The Proc GLM does it. Okay, so now this is an easier way to get it to compute a risk. You still have to compute this ratio yourself, but SAS is going to automatically spit out the risks. And then all you got to do is compute the risk ratio. So this is the risk of under the exposed, and this is the risk under the unexposed. Okay, so that's getting cooler. But we can't get the standard error. So there's a big catch, which is these are all about computing the point estimate. And SAS will not, unless you do a lot of torture that I almost once completed to get the standard error, but I gave up because Sudan does it. You actually can't get the standard error of that ratio. Why do we want the standard error? The standard error is what we need for hypothesis testing and the confidence interval. So the best we can do in SAS is compute the risk ratio. Okay, but this is ways to quickly get it. So if you're in SAS and you don't have Sudan, you're on the desert island with the fractures that we talked about, and you have SAS but you don't have Sudan, your license expired, and you can get a risk ratio, but you can't get the standard error of it. This thing is the standard error of the mean, but this does not readily convert. You can't readily use this to get the standard error of the ratio of the means. Okay, so you can get the risk. You can get a confidence interval on the risk, which is kind of cool. So you can, but it's not the standard error of the risk ratio, which is the single summary thing that's probably more useful. This is kind of useful. You could maybe make a confidence interval for the risk and talk about that. Here's the risk when people are exposed. It's 48%. It's 16% when they're unexposed. But you're not going to get the risk ratio directly. All right, so we got to use Sudan. What is Sudan? Have people taken any of the survey analysis courses? None of you? Some of you? Come on. If you're going to go work for CDC or many organizations that do surveys, you got to do it. Take the survey course. I'm not your advisor. Don't listen to me. But it's so useful. The survey procedures were so useful to learn, and I wish we had them more in our courses in EPI. If you can, take Paul Weiss's class in survey analysis. Sudan is a package that was developed as a standalone package, but also as an add-on to SAS. That analyzes survey data, weighted, complex sampling, cluster surveys or, various probability survey data. And it contains versions of proc means and freq and linear, the proc reg and logistic. It has versions of all of these that deal with complex sampling and weighting schemes. By the way, SAS now has versions of all these too that deal with them. They're called survey freq, survey means, survey logistic. They're actually better than the Sudan ones. So there's not much reason to use Sudan in my personal opinion, except that Sudan computes the risk ratios in cool ways that SAS still doesn't do. And you have this thing, if you go into Citrix and you are in SAS, you can actually type Sudan syntax inside your code. It's called SAS callable Sudan. And I'll show you what that looks like. So you can actually, you didn't know, but at your fingertips, you've always had Sudan. It's just sitting inside of SAS. You can use all of these procedures even when your data is a regular data set that's not sampled in any fancy way. You can still use all of Sudan's procedures on a standard data set. And we'll talk about that, how to do that. And our beloved IT department often lets the Sudan license lapse, and if that happens, you just send them many upset emails, and then you get it back. So it's not very well maintained, but it's there in the background. And if you harass them enough, they'll renew it. So here's what it looks like. So we're going to use this thing called Proc Logist. Logist is Sudan's version of logistic regression, and it's got syntax that looks more or less like the SAS Proc Logistic syntax, and we're going to use it to compute the conditional marginals risk ratio and its confidence interval and its hypothesis test and all that fun stuff. So the model line, exactly the same. Here we go. Let's follow what the slide actually says. We're going to first start with that. Design equals SRS. This is telling Sudan, I have a regular data set that is a simple random survey, as in an unweighted, there's no weights, everyone was sampled equally in this data set. So you have to first tell it, I'm doing a regular old analysis. Got to do it, because otherwise it's going to expect you to specify the weights and the clustering and the nested stuff and all this stuff that has to do with stratified sampling. So you want to do this. Then when you do the class, it has a class statement. So you want to do class. To do the conditional margin statement, which we'll get to, the exposure has to be categorical, right? Makes sense. You don't compute a risk ratio on a continuous exposure. Does it make sense? So you have to use the class statement. In Proc Logistic, we can get away without the class statement on the exposure if it's just 0, 1. Here you got to do it. And you got to do this extra line called reflev equals 0. This is going to set, this is like the ref equals option in the class statement on SAS. You have to do this because it has to know what the comparison group is. This is saying exposed is 1 versus unexposed 0. So you got to do this as a second line, reflev previous hosp equals 0. Okay? Then we're going to do this thing. Cond marg, that's conditional margins. Prev hosp, that's the exposure. And again, you have to put in the 0. Don't ask why. You have to do it twice. Okay? Just, it is. And you're going to say slash adj_rr. What is that? Adjusted risk ratio. Okay, so that's, you're saying I want the conditional margins, I want the adjusted risk ratio. If you don't do it, it just gives you the adjusted risk, so we don't want that. This is basically very, very similar to what that LS mean statement was doing before. It's the same idea, but it's going to give you the confidence interval, which is really cool. Okay, so you got to do this. Otherwise, it's more or less what we know from Proc Logistic. Very little is changing. You got to add this extra line, 2 extra lines, but more or less it's the same thing. And then you get this. First of all, Sudan does not use the SAS ODS system. So it's going to give you, old school format SAS, which is in the output window, not in the HTML window. There's all those windows. This is going to be text, and it's in the output window. And it's going to look like this. This table is the table of the beta estimates. Okay, so in SAS, it looks like this, 2.4, blah, 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 blah. Here it is again. Okay? Same thing, same information, more or less. But this is Sudan's version, so that's cool. So you're first going to get that. Then you're going to get a table of odds ratios. This thing, which we said is only sometimes useful because sometimes the odds ratio is way more complicated than e to the beta. Here's a table of e to the betas. And you get the same old thing. Here it is. In Sudan, it gives you some extra useless things like this, 1, because it's the reference group. So I don't know. But here, 5.14 is the exposure odds ratio in this model. And the 4.28 is e to the gamma here. And it's the same business that you get in SAS. Then you get this other cool thing, which is the table of the risks, the estimated risks, which was the LS means table that I showed you in SAS. And these are the estimated risks at each of the exposures, 0.49, 0.4884, and then 0.16. Okay, so this is the risks, but it's not the risk ratio. But then you get this thing. This is really cool. Here we go. Those exclamations, sad faces. What's going on? This is a table of the risk ratios. And you get 3.12 and a standard, and you get the confidence interval of 1.76 to 5.56. So this is the holy grail. We wanted a risk ratio on the confidence interval for it. This is exactly the 3.12 we saw earlier that we manually computed, but this was not present. So now we get a risk ratio on its confidence interval from SAS/Sudan. Sudan called inside of SAS. So one thing you might do is you might do all this cool work in your, you might do all this work with your model, and you have a final model that you like. And by the way, you might want to report risk ratios from it. You could imagine putting Sudan code at the end of your analysis to start reporting the risk ratios as well. And you might put it in this here at the end, and you might. That's kind of cool. We got risk ratios. So, but there's more. The more is that there's actually a better way to do this than the conditional method. The conditional margins method was conceptually straightforward. Plug in the mean for all the v's, and that solves your plugging in stuff for the v's problem. Just compute the means of all of them. It's easy to compute. But the con is that this business of plugging in the prevalence of binary variables rather than zeros and ones is conceptually bizarre. And there really may not be, such a person that, even if it was okay to plug in 0.22 for smoking, which I still think is weird, you're imagining, the analysis is computing the risk at an average person at every single average value of all the V's, okay? What if your data really has no such person that's an average person? Some people are high on these things, low on that, or everyone's kind of all over the place. But there really, truly are no average people, right? There's so many different V variables. And what if it's conceptually, what if there really are no such average people in the data? You're really making up a fake person that was never in the data set and saying, let's estimate the risk at the values of this fake person when they're exposed and unexposed. Does that make sense? Like you're making up something the data doesn't have. And so that really might be extrapolating from what the model is really fitting. The model is fitting to your data set, which has its unique people, and you plug in a totally fictitious average person that doesn't exist. So you often get estimates that are in the ballpark, but not exactly equal to more accurate methods, which the stratified and the predicted margins method are pretty much, I think, going to be as unbiased as you get. And this method is pretty good, and it's going to be in the neighborhood of the truth, and it's quick and easy, and you can explain it to your grandparents. But the other more complex methods are going to make more sense from a bias perspective. This maybe give you an unbiased weird thing because you're plugging in these made-up values. So we're going to talk about a second method that's similar but different. It's going to involve clever ways of plugging in things with the V's, but it's not going to be plugging in the V bars, the average value. And here's the idea. We've got a model that predicts risk. All right, it predicts risk, it predicts odds. It's our logistic regression model. Here it is. Predicts the risk. Here it is. We're going to simulate the counterfactual risk for every single observation in the data set under exposed and unexposed. Okay, why on earth would we do that? Do you remember way back with the babies and the cloning of babies and the sheep and all of those slides? The thing I was talking about then was in an ideal world, we would have a clone of everybody that didn't get the exposure, right? That's the ideal, right? We would do this, thing where everyone, it was a clone. We had all these clones, and half of them are exposed and half of them are unexposed, and that balances all the confounding stuff, right? In some way. And where everyone is observed under both conditions of exposed and unexposed. That's really the ideal. Well, we have a magic risk machine called the logistic regression model. And you can imagine, you could calculate, if this is the best model, if this is truly the best model you think is the best, if you believe this model to be an actual, fortune-telling machine, because it's the best model, you did all of our EVW stuff that we said, and it tells predictions of risk, then what if I computed the risk under exposed and unexposed for every observation of the data set? And I would get basically two samples, the entire data set under exposed and the entire under unexposed. Well, if I compared them that would be pretty close to my ideal cloning thing. I take the data set, I predict them underexposed, predict them under unexposed. If I took the ratio of that, that would kind of be the idealized, that would be, as using a model, the best thing I could do to cloning folks. And that's what this method of the predicted margins is going to be about. So we're going to take this, presuming this is the model, we're going to take each person X, and we're going to say, okay, your person X was exposed. We're going to take their covariates. Let's say I have a person that was PAMU1 and sex 0. This is respondent 26. We're going to say, let's pretend respondent 26 with their covariates was exposed, compute their predicted risk. Now we're going to pretend they're unexposed, compute their predicted risk. Okay, that's the basic idea. We're going to do it for every observation, and now we're going to take the ratio of what you get under exposed and unexposed. So we're using everybody as their own control, and we're going to predict the probabilities. Okay? So again, we're going to do this for every observation. We're going to compare the average predicted risk, assuming everyone's exposed versus assuming everyone's unexposed. So this is actually simulating the thing we really would love to do as epidemiologists, which is give everybody exposure and non-exposure and compare their response. We would love to do that, but we often only get one shot at this in an observational study, which is the exposure they had. But now we're going to also give them the thing they didn't have. Okay? And if this fortune-telling machine is correct, then we're going to get an unbiased estimate of the risk ratio. Pretty cool. So this is simulating the counterfactual, which is actually what we would love to have as epidemiologists. Okay, so here's the idea. Here's the same output, alpha hat, beta hat, gamma hat. For somebody who is exposed, okay, this is the formula of their predicted risk, right? You have alpha hat, beta hat times exposure equals 1, and then 1.45 times PAMU. This is the same stuff we saw before. And this is the formula of the risk when you're unexposed. It's the same thing minus the, take this out, the 1.64, it's gone. Take every observation in your data set. Here's person 8, they have exposure. This is the, this is the outcome, I'm sorry. This is the MRSA outcome. This is the Y variable. This is the two X variables. This is the exposure, and this is the V variable. And for each row, you plug this person's exposed. Okay, so we're not going to deal with that. This person has PAMU1. They're going to plug in here. For this person, we're going to compute the probability of exposure when the probability of the outcome when they're exposed versus when they're unexposed. So this formula, given this value of PAMU, is 1. So we're going to get 0.65, blah, 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 versus 0.267, blah, blah, blah. This is for this person who had PAMU1. This is their two counterfactual predictions. When they're exposed, this is the predicted outcome. When they're unexposed, this is the predicted outcome. Here's somebody that has PAMU0. Okay, so now their risks are different under exposed and unexposed, right? They don't have PAMU. They have a different value of this. These are their two values of these two formulas. Notice these people have the same predictions as each other and as the first observation. Why is that? Because they have the same PAMU value of 1. See? So in this model, there's only two predictions that you can get, right? The only V variable is PAMU, and it's binary. So you're going to always get the same two pairs. That makes sense? The formula only has one variable in it. That's it. You're always computing exposed versus unexposed, okay? So you're actually ignoring the exposure column because you're pretending everybody was exposed and unexposed. In reality, right, this person was only exposed, this person was only unexposed. We're throwing that away and we're pretending they were in both conditions. Okay? So that's the idea. We're making up a game here. It's not the actual prediction based on the exposure they had. We're using both exposed and unexposed. And the point of this game is we're going to do this. We're going to take the average risk of the data set given the average risk in the data set when they're exposed. And that's this. The sum of these probabilities over n is the average risk when they're exposed. And you're going to take the sum of this column over n, the unexposed column, and that's the average risk when you're unexposed. And you're going to take the ratio of that. That's the risk ratio. Okay? Average risk, risk ratio. It's the ratio of the means of the above columns, okay? So it's the sum, it's going to be the sum of every person's predicted probability under exposure over the sum of the predicted probabilities under unexposure. Don't worry, Sudan will do this for you. Right? I'm just showing you the idea. This is tedious. This is not fun. And I wrote the PX. I did this in a data step. You're not going to have to do this. This is just me. Okay, so this is a really beautiful idea. This is really intuitive. We have a model that makes predictions, predict everyone under exposed and unexposed, take the ratio of it. This is simulating the thing we'd love to do in real life. Okay? So we can trick SAS to do this, like I've done here. And again, you can get the risk ratio by tricking SAS to do this. But you won't get the standard errors. And again, you need Sudan to do that. Okay? And it's the same exact code as we saw before, but there's another statement called pred_marg for predicted margins, and that's it. I will just do it for you. So we'll show you what that looks like. Same code for the ref_lev and the pred_marg. Why is it red? Right? It looks like you've done something wrong. Well, the code for Sudan works in SAS, but it doesn't highlight it appropriately for you. So it's going to highlight syntax in blue that it recognizes. It doesn't really know. It doesn't know from Sudan really. It's a plugin, and so it's going to yell at you like you're doing the wrong thing, but it's going to run. It's just going to give you red code. And so what you get here is this output. You get all those other tables previously, and now we get something called the predicted marginals table, 1 versus 0, 2.73, and with a confidence interval of 1.55 to 4.81. Okay, so this is the 95% confidence interval. Notice before it was 3.12. That was when we got with conditional margin. So we actually get a different answer. They're both 2.7, 3.1. It's kind of in the same zone. But this is probably the more truthful answer. This one had that weird assumption, which is that you're plugging in average people that don't exist. This is actually it's actually the same idea, but in reverse. In the conditional margins, you compute the average first and plug it in and see what you get. This has weirdness to it. This is the average value if you don't plug it in. If you plug in the actual observed values of zeros and ones. So it's whether you take the average of the V's first or compute many risk ratios and then take the average after. It's the same idea, but kind of in reverse. This one is unbiased. This one has a weird bias of making up people. Both of them involve an average, but this one, again, like I was saying, you use the observed values of the V's, but take the average at the end. That's all you're doing, rather than the average on the V bars. It's where you take the average that matters. And this one is cool because it actually kind of flows from epi thinking of we like counterfactuals. So I like the predicted margins approach, and I think it's less biased. This gets complicated here, right? When we think about many V variables, right? You're going to have many, many covariate patterns. Right, so here, backing it up, sorry. Right, we only had 2 possible values of this because there was only 2 covariate patterns. This is where the ROC lecture is helpful. Right? The covariate patterns are all the ways you can make your X variables. Or there's only 2 covariate patterns for the V's, I should say, because we were ignoring the exposure. But as things get more complicated, we add more V variables. We have more covariate patterns that involve the V's. And we're going to get unique intersections and predictions for every row. And the predicted margins methods deals with that. It computes for all the people, however they come to you, with all their V's and whatever that means. It predicts all of their risks and takes the average at the end. So I think that's very cool. It comes up with a way of naturally just using the data that you have to compute the risk ratio. So here, this changes. Notice this is the different value. This is not 2.7, it's 2.24, because I've controlled for more stuff and I get a different answer, just like I'd get a different odds ratio. And so, again, it's still, you can add more V's and use the same syntax. You've just changed the model line, and you get a change in prevalence ratio. You can actually imagine doing model selection not with 10% change on the OR. What about 10% change on the RR? You can do it. We're not saying you can't. You may want to consider a different threshold for change because remember the odds ratio moves easier. You get 11.7 really easily. So maybe you want to say 5% change in the RR, or whatever makes more sense to you. There's no rules for this. But the RR is harder to move than the odds ratio, which is more wild when you have a non-rare outcome. But you can imagine you can do everything, all your model selection in Sudan by taking things on and off the model statement here and computing this pred marg and looking at the change in risk ratio. So really there's two methods for this. There's the conditional and the marginal. The conditional is kind of straightforward and like intuitive, just plug in the means for everything. This one is kind of cooler and maybe I think less biased. And again, it's compute the risk at the average, compute the risks at the average V's, or compute all the risks and then take the average at the end. It's where you take the average. That's all it is. I think this makes more sense. They both work in Sudan. It's pred marg versus con marg, and that's it. Okay. With effect modification, this gets a little weirder, right? Just like with the odds ratio, there's a different risk ratio at each value of the W's. Remember, the odds ratio, we had to specify the effect modifiers because the effect is modified by the W, so you have to actually specify the value of the W. You need to do the same thing with doing risk ratios, right? The risk ratio, when you have a product term in the model, is going to change as a function of this W variable. Same business. So it will work. Sudan will let you do it. I'll show you the code to do this with effect modification. It does not work with continuous W's. That's the only caveat. If you have a continuous effect modifier, Sudan won't do this, and it's going to get upset. So if you have a continuous W, I don't really have an answer. So the code looks something like this. Like here, what if there was effect modification with sex? So you have to put sex on the class statement. It won't work without it like I said, it won't work with continuous variables. It has to be on the class line. And here is what the syntax would be for the risk ratio when sex is 0 and when sex is 1. Okay? So this is so imagine, you want to say, I want the effective exposure at the two levels of sex 0, sex 1. This is the way you do it. You have to write it prev-hosp 0, parentheses 0 times sex 0 / edge RR, and then here sex 1 edge RR. Okay, and it's going to give you, Sudan's not so smart. It's going to give you some things you don't need and some things you do need. So let me show you how to read this. This table is the output for this first statement. The way I know that is it says right here, when sex equals 0, what is the effect of prev-hosp 1 versus 0? That's the thing we want. That's the risk ratio for the exposure, 1 versus 0. When sex is 0, okay, 2.66. So that's the first thing of interest. It also gives you, for this line, something you don't care about, which is this other thing, which is use the variables in this way, and it's going to give you this thing you don't care about, which is when prev-hosp is 0, sex 1 versus 0. That is like flipping the 2x2 table the other way. It's like using the wrong and non-informative comparison. So don't use that. You got to read this really carefully because it gives you the sex risk ratio. It's basically giving you the sex risk ratio when you're unexposed. When you care about the effect, yeah, you got it. So don't use this one, and then this is the effective exposure when sex is 1, and then don't use this line. Okay, so this is how you do it with effect modifiers. Okay, I'm going to try to breeze through this because I really want to show you this cool thing in SAS. So the rest of the slide set has less things I endorse less, basically. Okay. That's all I'm saying. So there's the stratified approach, which is going to be very, very similar to the predicted margins, but isn't actually implemented in any statistical package. So it's a conceptual thing, and it exactly equals the predicted margins approach when you have categorical V's. If you have continuous V's, it doesn't work. And this is very conceptually related to the Mantel-Hansel method. There's some slides there. This is cool stuff if you want to reach some state of mental clarity on how this all works and how they all tie together. Go to the top of a mountain and read this. Okay. The log binomial method is the following. I want to just show this conceptually because this is used a lot in the world. There's a really easy way to get around this specifying V's business. It's called fit a different model. Okay, and it's called, you ditch the logit model, where we saw that the V's don't cancel, and instead you fit a different thing called the log binomial model, which is you take the log of P, not the logit of P. The logit's the one, the 1 over 1 plus, the minus. This is just the natural log. And it turns out, for many situations, this is actually a pretty okay model too. You still have the distribution of the residuals as binomial, which is an assumption of the logistic model, and also, but it's taking the log, and so instead of logit P equals blah, 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 it's the natural log of P equals blah, blah, blah. And here, you take e to this, right? E to this is P. E to the log of this is P. So this is the probability is equal to e to the alpha plus beta and so forth. This is the log model. This is the regular probability model. And now this is the expression. This in the logistic model was odds equals e to the alpha plus so forth. Now it's risk equals e to the alpha plus beta exposure. And now the ratio of that becomes e to the beta. So in this model, all of the e to the beta stuff actually is the risk ratio directly, because you actually fit a different model. This is very similar, as we'll see in a few weeks, to the Poisson regression model, which is also a log model. This will give you often similar answers to the predicted margins approach. But you're actually fundamentally fitting a different model. Sometimes this doesn't fit the model well. Sometimes you get weird convergence issues, and sometimes the data blows up. The SAS will blow up when you use this. So one way around this problem is don't use a logistic regression model. Use a fundamentally different model, which is the log binomial model. If you have Sudan, there's no reason to do this because we have predicted margins in Sudan. So just use that. This is what you use to get a risk ratio with e to the betas when you don't feel like doing anything else, you don't feel like using Sudan, and that V's stuff is annoying. This is a way to kind of fake it. But we have the logistic model in Sudan that will help you with all this. All right, now I want to just switch to SAS. I want to show you something cool. I think it's cool. This is a thing I did last year, which I have to still modify. It's called Proc EVW. And it actually automates a lot of what we've been talking about in class, and it shows a couple new things that one day I'll make a lecture out of this when we get a couple extra weeks into the, you never go home for winter break, we can talk about this. It's something I haven't formally done because we don't have time for it. And here's some documentation, I'm not going to read this to you, but it does a bunch of cool things. It automates the EVW modeling process it does assessment of interaction, all subsets, and it just does it and shows you the result for your model. And it takes a whole bunch of inputs here. I'm just going to show you just, some of them are required, some of them aren't required. You need to, it's a macro, okay? So you're going to say % proc EVW, parentheses, data in, I tell it the data set. And you're going to basically tell it the stuff in your model. I'm going to say that the D variable is this, the E variable is that, here's the V's, and here's the W's. And this is all it needs to run, actually. And the rest are kind of optional things. In theory, it's going to do more than logistic regression. I just haven't finished it. I don't have the time. One day I will. So it's right now just as logistic regression. This is going to be something that I built it in. It's for Poisson regression. We'll talk about it. This tells it this is telling it what's on the class statement. And you could add extra stuff to the proc line or the model line, right? Because often we add extra options, and these are extra options you want there, like descending or whatever. You can set the alpha. And I'm going to talk about there's some sorting and cool other things, and you can give it, I'm going to show you what this all means. And then you can tell it whether you want to do selection of effect modifiers or not. You can turn off the effect modifier business. I'll show you what this means. Here's some examples. Cool. I'm going to put this on Blackboard. Okay. It's using our favorite MRSA data set. Okay, because it is. But you can use this for anything. Here's the most basic model. I'm going to run this proc. I'm not saying proc logistic. It's now proc EVW on my data MRSA. The outcome variable is methicillin resistance, exposure, previous hospitalization, 3 V variables, age, sex, PAMU. Okay, look at this. It's going to be really fun. Go. It's thinking, it's doing. Look at all that doing. Cool, look what it did. Okay. It did, I have 3, there's no interaction. So it did nothing about it. It knows to ignore interactions. Ignored interaction. Here's all subsets. Ta-da! Okay, D is this, E is this. Here are all V's. All 3. This is the what model? Gold standard. Gold standard model. Here's the gold standard model. It even tells you, look, see? It says, don't look at that, gold standard. And then it's going to drop 1 at a time, 2 at a time. And now this is the model that has no V's in it, so it dropped all of them at a time. So look at that. Here's all the adjusted odds ratios. Okay, and I think it's flipped because I'll show you what I'll show you. Yeah, this is. It didn't specify the descending option, which I think I add later. See, it's the opposite of what we wanted because I didn't specify descending. That's okay. Here it's showing the percent change from the gold standard. Here's all the things we used to make you do by hand. And then here it's showing all of the ones that are less than 10% change from the gold standard. Isn't that cool? And there's more. Here's a graphic of that, right? Actually, why did I have to make a table? I can make a cool picture. Here is a picture of the above table. This is the odds ratio for the gold standard model with its confidence interval, and here's plus or minus 10%. And anything that's in the zone here is in the unbiased zone, right? That's kind of cool. Is this cool? I feel fancy. I did this. So, you can look at the picture, and anything that's in the zone is in the unbiased zone. And then you can do this better than scanning the table, or it's make at least something you can show someone and be like, here it is. Here, precision assessment table, because up here was about, remember, we don't want to assess precision yet. We're just going to talk about bias. Then what it does, it's so smart, it actually knows that these are the only 2 models we should go and think about. And then here's the precision assessment table that, for valid models within 10% of the gold standard, it gives you the width of it gives you the CI width and all of that kind of stuff. So this does everything we've been saying to do. So that's kind of cool. But it gets even cooler. So we can change things, like who said the 10% rule is what it is, right? You can change the alpha for the confidence interval in the statistical testing, and you can also change the criterion for the cutoff. So it's at 10% change is where it is now. You can do things like change the cutoff to 30%. Here, I'm going to show you a couple more things. I'm going to add this one. I think just adds a few more. But this shows you can specify logistic, but it doesn't really matter. This changes it to descending because that's actually going to give you what you want. And then I think this model details actually also spits out all of the stuff. I think it gives you a couple. Oh yeah, it gives you all of the Proc Logistic output along the way. Right? If you want to see all this stuff in the middle, you say model details. Here, this one changes the alpha and the percent cutoff. So you want to say, I don't care about the 10% rule, it's a 30% rule. It switches everything to be 30% change, and they even see it changes all the titles. It's fancy like that. And again, notice this is actually on the right scale. It's above 1. It's all 4.4, 11.6, and all of that. So you can control all of the pieces you care about. You can do class variables. And this, I don't think it effectively matters too much here, but you can do class variables as well. You can specify it doesn't matter. And so I want to show you how to do, the full backwards elimination process. Okay, so here I'm going to put W variables in, effect modifiers, sex and PAMU. So now it's going to also do the likelihood ratio test, not just the wall test, it's going to do the likelihood ratio test on all of the effect modifiers. Okay, and so it's going to look something like this. This is fancy, look at this. Okay, so it's going to do, is this it? No, this is the old stuff. Okay, it's going to do lots of likelihood ratio tests. It says full model is this. And I'm going to do this reduced model here. Actually, no, I think it was, but there was more output. And it's going to basically show you what happened. It says, here is a non-significant interaction. I'm dropping it. It starts talking to you. And then it says, I stopped. This is actually the last step. I think is it dropped. There was 2 steps up here. You can't even see it. It basically spits out a lot of output, and it dropped both of the interaction terms that I cared about. And then what you have to do is that you run it once to figure out the interactions, and then you run it again after you modify your model, and it will do confounding assessment. So if you have interactions, you have to run it twice. You do it once as EW selection mode, and it does all of the backward stuff, and with likelihood ratio tests, and then you run it again after you drop. You have to modify it in the way that you want to. The last cool thing I'm going to show you is this, then I'll stop because we all want to go home, which is what if there was a significant interaction term. Here, this code pretends that there's a W variable, PAMU, with 1 and 0. And now I need to look at tables of odds ratios, right? Remember, now it's the odds ratios under W0 and W1. You have to remember, and that was kind of annoying, right? Because you have to draw multiple parallel tables and have like split vision to look at it. This is gonna do it in a nice way for you. Okay, and what it's gonna do is give you, look at this. The top half of the table is under effect modifier 0, all of the odds ratios. Okay, and this is on the bottom 4 rows are under effect modifier equal to 1. How do I know? You can see it says this. PMU0, PMU1, and it has 2 gold standards. Look at that. And these are all comparing to the gold standard above it. And you got even a fancy plot of that. Notice the bands change. This is for the 0, PMU0, and these are for PMU1. So this is a quick way to scan the split vision thing when you have 2 golds, where you have the odds ratio and it's W0, W1. So that's kind of cool. This automatically gives you a way to do the split vision thing. When you have multiple tables, it will just do it. And you can also do other cool things. You can combine into one big, you can sort things different ways, and you can do all sorts of cool stuff. So I'm going to put this online. You have to play with it because the syntax is a little funky. This is basically what it says on the contrast line. This is how you deal with this. Right, this is how it knows how to make EVW, how to give you the split EVW stuff. This is saying give me under 0 and this is under 1, and this will explain it all. Anyway, that's all I got. I'll see you in a little bit.